Okay, so from class on Monday, Tuesday, you had kind of the sections where it went through how to determine what the charge on the central metal ion is in one of these complex ions. So there's sort of two categories, I guess you could say. If you look at the ligands, which remember those are the things that are out here around the outside. If the ligands are neutral, meaning they don't have a negative charge, okay, then whatever the charge out here is, that is the charge of the central metal ions. So on this one over here, all of the ligands are all water, and water molecules are neutral. They do not have a charge. Therefore, the iron in the center of this complex ion is also 3 plus charge. Okay. Now, if you have something that has a charge, you're going to have to take that into account and subtract it from the overall charge. So, for example, on this second one that's on here, all of these, there are 6 cyanides. So, all of these are CN cyanide, and there are 6 of them. Now, if you remember from previously, up here I gave you this list of potential ligands, and cyanide was one of them. And cyanide is a negative, has a -1 charge. And so I have to take that into account when I'm trying to figure out the charge on this iron ion in this complex ion. So what I would need to say is I would need to say, okay, my charge is, 3 minus, right? That's the charge from up here on the whole complex ion. And then I'm going to subtract -6 because there are 6 cyanide ions right here, and each one of them is -1. So total, that's -6. And then you have to kind of think about, okay, what happens when I subtract a negative number? And that means that it's going to go opposite. I'm actually going to be adding it. And so what this becomes is it becomes -3 plus 6 instead of minus -6, which becomes plus 6. And -3 plus 6, that's a positive 3. And so this iron is also 3 plus. Okay. So the iron's 3 plus, but notice that on this first one, the charge was the same on the complex ion. On this one, it was not. And that's because of the ligands on this one contributed some negative charge to the whole complex ion. Okay. This last one, there are only 4 ligands. They're all the same. They're all chloride ions, Cl. And so if you remember, again, back up here on our list of possible common ligands, Cl, chloride ion, is a negative charge. It's -1. So that means each of those chlorides that are on this complex ion is a -1. So that means there's technically -4 there. And so in order to figure this one out, I would look at the whole charge and I would say, okay, I have -2 minus -4 because there are 4 chloride ions. So it becomes -2 plus 4. And that means that it's a positive 2. And that means on this one, the copper would be 2 plus. So that's basically it. Again, like the first example, if the ligands are all neutral, then your central metal ion has the same charge as your whole complex ion. But if the ligands have a charge, like on the other two, you're going to have to do a little bit of math to take that charge, those charges into account. Okay. Okay, the second part of what you guys had on Monday, Tuesday was looking at these variable oxidation states, because we've seen that most, if not all, of our transition metals have multiple charges or variable oxidation states. So oxidation states is kind of another way of saying charges. The only really exception is scandium. Scandium's only +3. The rest of them typically all have multiples. In fact, when you watch the video online, nickel has a 1 and a 3 and a 4. It's not typed on here, but when you watch the videos notes for online, if you haven't already, their chart looks a little different than this, but you could go ahead and add in if they're missing any. And the one online also shows you their electron configurations with their orbital diagrams. And so you can see sort of kind of why they have multiple charges or why they have the number of charges they're able to have. And it has to do with the number of like unpaired electrons and things like that. Okay. Because as we go up to manganese, notice that there's, 3 charges, then there's 4 charges. And then I believe when you look on the video online, chromium actually has more than those 3. Okay, it has 4 or 5. And I think it has 5, and then manganese has 6. But then it starts going back down with iron and cobalt and nickel, all the way down to copper, where copper only has 1 and 2. And then zinc, remember we talked about the zinc, technically by our definition of transition elements, it doesn't fit that definition because it doesn't have any unpaired d electrons. And so that's why zinc only has 1 charge, because it just loses the 4s electrons. It doesn't lose any of its d electrons. But all of these other transition elements that fit that definition of having an unfilled d energy level, or a d sublevel, excuse me, the reason that they can have all of those multiple ones is because they can lose different amounts of electrons. So all of the transition elements, okay, it says right here, except scandium, all the transition elements can have an oxidation state of +2. That's because they lose the 4s electrons first, and 4s can hold 2. So they can all have a 2+. After that, it really just depends on, how many unpaired d electrons they have, and how many they can lose, and that kind of stuff. And so, again, when you watch the video online, make sure you pay attention to what do their electron configurations and orbital diagrams look like, and how does that relate to how many possible oxidation states that they can have. Now, one thing is it shows you this graph where we're comparing the successive ionization energies in 2 different elements, calcium and chromium. And if we look at where they're located on the periodic table, calcium, they're both in the 4th period. Calcium is, let's see, I'm going to write it up here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's calcium. Calcium ends with 4s2. Now, if I go on to chromium, chromium is the one that it's an exception. So chromium is 1s2, 2s2, 2p6, 3s2, 3p6. Now, normally it would be 4s2, but chromium is one of our exceptions. So it's actually 4s1 and then 3d5 instead of being 4s2, 3d4. The difference between these two, calcium is a regular metal. It's not a transition element, because I can see that if I look at this graph, calcium has its its ionization energy. There's not really a big increase, but then all of a sudden, after that second ionization energy, there's a big jump for calcium. And so when the third the third electron is removed, it has a large increase because it's going from 4s2 to now that third electron is coming from right here in the 3p sublevel. And so it's going to require more energy because that's closer to the nucleus and it's being held more tightly by the attraction. For chromium doesn't really, it's pretty steady. It doesn't have a huge jump until we get to the 6th one. Between the 6th and the 7th, it has a big jump there. Okay. And the reason is, it says right here, it's due to the closeness of the 4s and 3d sublevels. And so even though it's losing the 4s, the 2 that are 4s first, and then these are all 3d, they're so close in energy that there's not a big jump or a big difference in the amount of energy. So it's fairly stable until it gets rid of all the 3d. So it'll lose all 6 of these, the 5 that are in 3d and the 1 that's in 4s. It'll lose all 6 of those. And then when it goes to try to lose a 7th one, this one right up here, that one's coming from 3p. And so just like with calcium having the big jump back here, chromium's big jump is over here, but both of them are going from, like 4s to the 3p. Okay. And so because of the fact that the 4s and 3d sublevels are so close together for chromium, that allows it to have those variable oxidation states like the other transition elements do as well. A couple of properties for transition elements, magnetism, and then we're also going to talk about catalytic properties. The reason things can be magnetic, specifically transition elements, is because of their unpaired 3D electrons. So if we were to compare some, and when you, if you watched the video on Canvas already, they actually showed you physical examples of compounds that contain these 4 metal ions, and they compared how they were attracted to a magnet. Okay, and so there's a couple different definitions here. Paramagnetic means that they have unpaired electrons. Okay, those are the ones that are going to be attracted to a magnet. If something is diamagnetic, it has no unpaired electrons. So that means it's not magnetic. It's not going to be attracted to a magnet or repelled by a magnet. Okay. And so the ability of something to be kind of attracted or repelled has to do with how many unpaired d electrons it has. So when you watch the video online and they show you the magnets, they show you that the magnet has no effect on zinc. It doesn't repel, it doesn't attract, it doesn't do anything. Okay. That's because zinc doesn't have any unpaired electrons. It's diamagnetic, which means that it's not going to be attracted because it has no unpaired electrons. And then for the other ones, as you go, if you notice, this one's got 1, this one's got 2, and this one's got 3. So as you go down, the number of unpaired electrons is increasing from copper to nickel to manganese. And if you notice, the attraction of the effect of the magnetic field is going from weaker to stronger. Okay. And so the number of unpaired 3d electrons affects how much the magnetic field can affect that ion. Something like copper, it is going to be attracted, as you'll see in the video online if you haven't watched already, but it's very weak. Okay. And then nickel's a little bit stronger, and then manganese is the strongest one. And so basically kind of our takeaway is that to kind of be attracted to a magnetic field, you need to have unpaired 3d electrons, okay? And then, or unpaired d electrons just in general. And then more specifically, the more unpaired d electrons you have, the more attracted you're going to be to the magnet, or the more affected you're going to be by the magnet. And that's what they kind of show us in the examples on the other videos that you guys already have on Canvas. And then really this is just summarizing what I said, that the manganese has the strongest paramagnetic effect. Copper shows the weakest paramagnetic effect. Zinc is diamagnetic because it does not show any kind of effect in the magnetic field. Okay. And then when you have increased number of unpaired electrons, you have an increasing paramagnetic effect, or an increasing attraction to that magnet. Okay. Catalytic properties is the last thing from previous class. Okay. Catalytic properties, first off, we need to understand the definition of catalyst. So the basic definition of catalyst is it's a substance that provides an alternative reaction pathway with a lower activation energy. So what that means is it's going to speed up a reaction. It's going to make it go faster. And so catalysts can either be homogeneous, meaning they're going to be in the same state as all the other substances in the chemical reaction, or they could be heterogeneous, which means they're in a different state. Okay, so maybe, you know, your reactions are solutions and your catalyst is a solid. Okay, or your reactions are aqueous solutions and your catalyst is a gas. That would be heterogeneous. Homogeneous is like they're aqueous solutions and yours is an aqueous solution as well. Okay, or yours are gases and then the catalyst is a gas. Okay. So transition elements, they can all act as one of these types of catalysts, either homogeneous or heterogeneous. So there's just some examples of where you might see them. So for heterogeneous, a lot of these are used in like manufacturing or like industrial type of things. So the Haber or the Haber process is how ammonia is made. And so they use iron to speed it up to make it go faster. Okay, because anytime companies can speed up reactions, that's going to save them money, because the faster they can produce stuff, they're going to make more product in less time. They're going to be able to sell more of it. Okay. Nickel in the hydrogenation of margarine. So hydrogenation is something we learn about when we get to organic chemistry, which is topic 10. But hydrogenation is where you're adding hydrogen atoms or hydrogen ions to a chemical structure. You're hydrogenating it. And so that's how they make margarine. And so nickel being present in that reaction speeds that process up as well. Palladium and platinum in catalytic converters. Catalytic converters are these things that they will put on older cars that may be giving off like too much smog or too much pollution. So older cars where they have older engines, sometimes they tend to give off a lot more exhaust, a lot more pollution. And so they put these things, they can install these things on the car called catalytic converter. And what it does is it helps the environment, it prevents it from making as much pollution as it would normally. And so these two elements are usually present in those because it makes it go faster. Manganese dioxide in the decomposition of peroxide. If you've ever watched one of those videos online where they like mix things together and all of a sudden like something like explodes, what they've done is they have mixed together some hydrogen peroxide and like usually some soap and food coloring to make it all fluffy. But what they've done is they put some manganese dioxide in it, and that speeds it up, and that makes it decompose like really quickly like that. And that's where you see that stuff explode, and it looks like it just goes everywhere in somebody's yard or something like that. And then vanadium pentoxide in the contact process. That's another process similar to the Haber process. It's an industrial process for making substances. So for homogeneous, the two that are on here, they're actually pretty important. Iron and hemoglobin, and specifically it's iron ions, okay? If you are low in iron, you are going to be anemic, which means that your blood does not get enough oxygen to all of your cells and all of your organs like it needs to. And so this happens a lot of times. It's more common in women than it is in men, but anybody could be anemic. But if you don't have a high enough iron level, sometimes you have to either eat more foods that are higher in iron so that your body gets it, or you can take iron supplements. Like I know I have to take an iron supplement a couple times a day because I usually am very low in iron. And so what happens is if your body doesn't have enough iron in your blood cells, then the hemoglobin in your blood cells, it doesn't carry as much oxygen. It'll still do it, but it won't do it as quickly. So it doesn't carry as much oxygen. So this doesn't happen as fast. And therefore, and you start to feel like really tired or lethargic and things like that. And it can lead to other issues as well. But usually being tired or being fatigued is kind of a big indicator. I think you can have like discoloration of like your fingertips or your lips if it's really bad. And then the other one is cobalt ions for in vitamin B12, because this is another thing important for us, for humans, is that it allows us to produce red blood cells and have a healthy nervous system. So like all of our nerves, our brain functioning, our spine, our ability to move and all that. And so if you don't have enough cobalt in your body, along with B12, then these functions may not work right. And you may not have enough red blood cells, which can affect your immune system. And then your nervous system can be affected. So like you might not have as good response times because your nerves and all that stuff are going to be a little delayed or whatnot. And so that's why you always see people who are like, oh, have you taken your iron supplement or your magnesium supplement or whatever? Like if you look at any kind of drugstore, like there's all kinds of bottles in the vitamin section that there's like iron, there's magnesium, there's calcium, there's cobalt, there's manganese, there's all zinc, there's all kinds of different supplements that have these types of transition metals in them because they're important. They act as these catalysts and they help a lot of our bodily functions, and they just help us to be healthier and things like that. Okay, so on to the new stuff for today. So this is kind of the last part of HL. So I'm going to go ahead and scroll down. Okay, so I mentioned briefly, I think last week, that the transition metals, they can be really different colors. They produce a lot of different colors. And so the question is, well, why did the complex ions that these transition elements form, why do they make different colors? Why do they form different color compounds? And so it has to do with, it goes back to our atomic structure with our electron configuration and the amount of energy and stuff involved. So, when light passes through a solution of copper 2+ ions, certain wavelengths of light are absorbed and certain wavelengths of light are transmitted back to our eye, okay? So normally this complex ion, which is hexa-aqua copper, okay, because it's got 6 water molecules bonded to it, it appears blue. It's a very bright blue solution. And the reason that it's blue is because blue light's being transmitted to our eye, so the solution appears blue to us. But if we actually look at the wavelength of light that's actually being absorbed by the solution, red light, or the ones close to red light, like on this graph, I can see that it's kind of like red to kind of red orange. That's the wavelengths of light that are being absorbed. This says absorbance over here. And so if red light's being absorbed, then that means it's more like blue violet light that's being transmitted to our eye. Now, so this is kind of just a picture of what the solution would look like with the copper ion in it. And then this is showing you the complex ion over here with the 6 water molecules. So why does this happen? Well, the reason that they form different colors, they're not just clear solutions like some other compounds when you dissolve them. It has to do with the ligands when they bond to that central metal ion and create the complex ion. Because when the ligand comes in and it bonds, it repels some of the d orbitals, okay? And so what happens is normally there's 5 d orbitals, but when the ligand comes in and bonds, it causes those 5 orbitals to split. And so 2 of them end up sort of going up to a higher amount of energy or higher energy level, and then the other 3 stay down low, okay? And the difference in energy, that creates a color of light, because as we talked about in topic 2, we can use energy to solve for like the wavelength of the light, or we can also use it to solve for the frequency. And so if you know the energy, you can calculate technically the wavelength of light, and then you could look up what color that corresponds to. And so the transition metals are really the only ones that do this, because they're the only ones that have these D sublevels that are not totally filled. So elements like, sodium and potassium and magnesium and calcium, when you have those things dissolved in solution, the solutions are just going to be clear. They're not going to be any kind of color, because there's no of this splitting of d orbitals, there's no energy difference and that kind of stuff. And so what happens is electrons can transition from the lower, so they can transition from the lower to the higher up here, and that energy, the amount of energy that's needed to change that corresponds to a certain color of light that's being absorbed. So it's absorbing this much energy, and it's allowing the electron to jump up, and the amount that absorbed corresponds to a wavelength and a color. So in this case, this amount is going to fall into this area of the wavelength, 650 to 700, which is approximately where you'd find like red and orange light colors. And so the complementary color, which a complementary color of orange is blue, is what's transmitted, and that's what our eye reads. So to know it kind of goes along with, if you've ever taken art, we have our complementary colors. So red over here, if something is absorbing red light, then to our eye, it's going to be transmitting green light, and it's going to look green to us. If something is absorbing more in the orange range, then it's going to appear blue to our eyes. If something is absorbing in the yellow range, then it's going to appear to our eye as if it's kind of a violet color, kind of that purple violet. And so whatever light color we see, the opposite or the complementary color is what is being absorbed. And so those are the wavelengths of light that are being absorbed that you could use to calculate the amount of energy. And so our basic takeaways from this is we just need to understand that because the transition elements have that incomplete D sublevel, that causes them to be split into 2 sets of higher and lower energy when a ligand comes and tries to bond to the central metal ion. And the energy difference between those 2 sets of the d orbitals corresponds to a wavelength of visible light. And so then what we see is the complementary color. So again, if I see yellow, that means it's violet light that's being absorbed in that area, in those nanometers. And that's basically kind of what it summarizes up here, that the complementary color, what's being absorbed is what's transmitted from the color wheel. So you'll use that color wheel to figure out the opposite. Okay, so now what can affect the color of the complex ion? So there's 4 main things on here. The 2 that we really focus on are the identity and the oxidation state. So that's why you need to be able to identify what the substance is in the central metal ion, and you need to be able to deduce the oxidation state, because sometimes something is +2, it's going to be one color, but if it's +3, it's going to be a different color. Okay. And so we just need to understand that the identity, like if it's cobalt versus iron or manganese versus chromium, it's going to be different color if it's a different type. But then if it's like chromium +2 and chromium +3, those are probably going to have different colors as well, because the oxidation states are different. The identity of the ligand, that also plays into effect, and we're going to talk about that in just a minute. And then the geometry of the ion affects it, but we're not going to get into that into a lot of detail. So here is more detail about the oxidation state. And again, I'm seeing here, the key difference here, guys, is that this one is 2+, this is 3+. They're both water molecules for the ligands. And so that means that this one is Cr2+, this is Cr3+. They're the same as the complex ion charge because the water molecules are all neutral. And so it says, deduce the oxidation state of the metal in each of the complex ion and then explain why they're different colors. So I kind of already helped you with the charge. One of them is 2+, the other is 3+. And so in order to kind of explain, it says, as the oxidation state increases, the amount of splitting the d orbitals also increases. And so if you have example on here, for if you're going from chromium 2 to chromium +3, that increases the difference in energy. And so higher energy is going to mean a shorter wavelength. Okay, so this goes back to topic 2. So higher increased energy means a shorter wavelength. And shorter wavelength are going to be things like blue and violet. Long wavelengths are like red and a little bit of orange. Okay, so red, orange is longer wavelengths, and then blue, violet, those are the short wavelengths. So if I increase the energy, then that's going to decrease the wavelength and make it more more towards violet than blue. So that's why this one, originally it was already blue, and when it increased to the +3, that gave it enough energy that it went from blue to violet, because it increased energy, which caused the wavelength to decrease from the blue area to the violet area. Okay. So the last section has to do with what we call the spectrochemical series. This has to do with the ligands. This series, it arranges the ligands in order of their ability to split those d orbitals in an octahedral complex ion. So the higher up, so like the more this way I go, the greater the splitting of the d orbitals. And so on this side where I have like iodine, bromine, and sulfide, I guess, there's going to be a lower energy difference. And so lower energy corresponds to long wavelength. So you're going to be absorbing more like red-orange stuff over here. Over here on this side, you're going to have higher energy differences, and that means shorter wavelengths. So over here, you're going to have more of blue-violet being absorbed. Okay. And so it says carbon monoxide produces the greatest splitting of the d orbitals, produces the greatest energy difference. And so since that one would be absorbing violet, you're actually going to see more of that yellow color because of that one. And basically it just says use the spectrochemical series to explain why the two complex ions below are different colors. Because if we look, they both have copper as the essential metal ion. Okay. They both have a 2+ charge on the whole complex ion. The difference here is that this one has 6 water molecules. Those are all neutral. So that means this is Cu2+, because it's going to be the same as the overall complex ion charge. This one, though, it has 2 of them that are water molecules, but it has 4 that are, 4 that are ammonia. And so on this one, it doesn't have a charge difference. It's still Cu2+, but this is where I would look at the ligands. These were all 6 water. On this one, 2 of them were water, but 4 of them were NH3. And if I come back up here to this spectrochemical series, here's NH3 and here is H2O. And so you can see that NH3 is higher on the spectrochemical series. And so because the one on the right has 4 NH3s, that is going to cause it to have a greater energy difference. So that's basically what it's kind of summarizing here. It says NH3 produces greatest splitting, therefore the greatest difference between energy in the two sets of d orbitals. And so that means that it's absorbing more energy as the electron transitions, and therefore the wavelength of light absorbed decreases as the energy increases. So what you see, or what you would see, is you would see this one would be of a blue or a blue-green color because it's absorbing red-orange light because it doesn't have as much of an energy difference, it's lower energy. The other one, we would see blue-violet because it would be absorbing more in the yellow range because the NH3 molecules that are attached to it are going to give it a little bit higher energy, a little bit bigger of an energy difference. Okay. So we are going to